Today we're graphing rational functions, and we're going to graph the y equals x over x plus 2. We're going to have to find the whole, the vertical asymptote, the horizontal or oblique asymptote, depending on which one it is. I'll remind you how to find the x-intercept and how to find the y-intercept. So recall that when we're finding a whole, that is where a factor on top cancels a factor on bottom, which in this case, there's not going to be a factor on top or bottom that cancel, so that there's none for the whole. The vertical asymptote, remember that that's where the denominator is equal to 0. So if we had x plus 2, we set it equal to 0, that means we would subtract the 2 over to the other side, and x would be negative 2. So at negative 2, we would have a vertical asymptote. Our horizontal or oblique asymptote, remember that comes from taking the highest power on top and dividing it by the highest power on bottom. And since x divided by x is 1, we have a horizontal where y equals 1. For the x-intercept, that's where we have y is equal to 0. So if we have a function where we plug 0 in for y, now we've got this fraction. So we would multiply both sides by this x plus 2, and we'd get that x equals 0. So our function has an x-intercept at 0, which now you can see that the y-intercept is also 0, but we're going to show you how to do that anyway. When you're trying to find the y-intercept, you plug in 0 for x. So 0 in all of the x's, that leaves you with 0 over 2, which is 0. So we have a y-intercept of 0 also. Now remember that this vertical line creates a boundary that nothing can cross. And as we get really far down in the positive direction, it gets super close to the asymptote, and the same thing in the negative direction. So if our dot is at 0, this thing is going to be really close to this line here. It's going to curve through this asymptote, and it's going to be really close to this line. Now, I could make a table of values, and I could plug in a bunch of numbers for x to get an exact curve, but I'm not going to do that. I'm just going to make you draw the general curve for this one. Now, we don't know what's going on over here, whether it's this bottom portion or this top portion. Should recognize that it is going to be this top portion, but if you don't, we can always pick a number that is an x value over on this side. So say I pick negative 3, because negative 3 is over on the left side of this vertical asymptote. So if I plug in negative 3 to my function, that would give me a negative 3 over negative 3 plus 2, which is negative 3 over negative 1, so I get 3. I plugged in a negative 3, I got an answer of 3, which means my function is up here like we thought it would be, and it curves close to both of those asymptotes. So here's another example. We've got 3x over x squared minus 9. Again, we're trying to find a whole, so 3x over x squared minus 9. This bottom would factor to be x minus 3 and x plus 3. So there's not a factor on bottom that cancels with the top, which means that there's no whole. The vertical asymptotes, those come from setting each factor on the bottom equal to 0, which means we'd have vertical asymptotes at 3 and at negative 3. For a horizontal asymptote, we take the highest power on top and the highest power on bottom. We divide them. We're left with 3 over x, which is a remainder. And so since this is a remainder, recall that y is equal to 0 because x squared goes into 3x 0 times. Here's our horizontal asymptote. For our x-intercept, remember we plug in 0 for y. So I could multiply both sides by x squared minus 9 to get rid of the denominator, and I'd be left with 0 is equal to 3x. So I would divide by 3 and get that x equals 0. So there's my x-intercept. My y-intercept, I plug in zeros for the x's. So on the top I get 0, on the bottom I get negative 9, and 0 divided by negative 9 is 0. So I got that point right there. Now again, we don't know exactly what's going on with this function because we only have one little dot. So what we can do, again, is plug in some numbers. So let's say I plugged in a 5. That would be 3 times 5 over 5 squared minus 9. So that would be 15 over 16. So that's really close to 1. I plugged in a 5, I got almost a 1, which means my function is up in this area. Now I'm going to do the same thing. I'm going to plug in a negative 5. So if I plug in a negative 5, I'm just going to make this part up here negative. And then my negative 5 being squared is still 25 minus 9 is still 16. This becomes negative 15 sixteenths, which is almost negative 1. So my function goes like this. Now, what's happening in the middle? We could plug in a bunch of numbers, or we could recognize that, hey, every time I have one of these vertical asymptotes, almost every single time they've been pointing in opposite directions. So most likely, since the right side is pointing up, this side would be pointing down, and vice versa here. This side is pointing down, which means this side is pointing up, and it should go through these down here through the point down here. I can always check that real quick by, say, plugging in a 2, right? If I plugged in a 2 instead of a negative 5, on the top I would get 6. On the bottom I'd get 4 minus 9, which is negative 5. So that's a little bit more than negative 1. So I plugged in a 2, I got a little bit more negative 1. So you can see we were guessing correctly, at least with this part. And we could do the same thing with the negative 2, if I made that negative and that negative. So on the top I'd have negative 6. On the bottom I'd still have negative 5. So that would be a little bit more than 1. So we were right in assuming that it looked like this.